Welcome to EDC Lab demonstration. I am BVV Satyanarayana, Assistant Professor, Department of ECE, Mission Institute of Technology, Bhimavaram. The second experiment in Electronic Devices and Circuits Lab is Zener Diode characteristics. Coming to the objectives of this experiment, at the end of this demonstration of Zener Diode, you will be able to draw forward characteristics, draw reverse characteristics, calculate static resistance, calculate dynamic resistance, identify cut-in voltage, identify Zener breakdown voltage. And the prerequisites are identification of diode terminals, breadboard connections, RPS initial settings, ammeter and voltmeter connections. The aim of the experiment is to study the Zener diode characteristics under forward and reverse bias, to calculate static and dynamic resistances, to obtain the cut-in voltage, to obtain Zener breakdown voltage. The equipment required are regulated power supply 0 to 30 volts 1 unit, DC ammeter 0 to 20 milliamperes for both forward and reverse bias, DC voltmeter 0 to 2 volts for forward bias, DC voltmeter 0 to 20 volts for reverse bias. Component required are Zener diode BZ 9.1, resistor 1 kilo ohm, breadboard and connecting wires. Description of the experiment. Zener diode is a two-terminal diode like ordinary diode. The two terminals are anode and the cathode. And Zener diode, it is heavily doped diode compared to the normal diode. If the positive terminal of the supply is connected to anode, negative terminal of the supply is connected to cathode, then the Zener diode is said to be forward biased. In this condition, the width of the depletion region and height of the potential barrier is lowered by forward voltage. Majority charge carriers from both sides of the junction crosses the junction and constitutes a forward current, which is very large. A small change in forward voltage can create a large change in diode current, and hence the forward resistance is very small. The minimum voltage required to create a reasonable current in the Zener diode is called the cut-in voltage. If negative terminal of the supply is connected to anode, positive terminal of the supply is connected to cathode, then the diode is said to be reverse biased. In this condition, the width of the depletion region and height of the potential barrier is increased by reverse voltage. Minority charge carriers from both sides of the junction crosses the junction and constitutes a reverse saturation current, which is very small. This current is almost constant with respect to reverse voltage, and hence reverse current it is very small. If suppose the applied reverse voltage is greater than the breakdown voltage, a sudden rise in current flows through the diode, but voltage across the Zener diode is constant, and hence the Zener diode can be used as a voltage regulator. This particular heavily doped Zener diode can be operated in breakdown region, whereas the normal diode it cannot be operated in the breakdown region. This is the circuit diagram for forward bias, and here we are using 9.1 volts breakdown voltage Zener diode, and the anode of this Zener diode it is connected to positive terminal of the supply, and the cathode of the Zener diode it is connected to negative terminal of the supply. And a voltmeter of range 0 to 2 volts is connected across the Zener diode so as to measure the voltage across the Zener diode. And a 0 to 20 milliamperes ammeter it is connected in series with the Zener diode so as to measure the current flowing through the Zener diode. And this 1 kilo ohm resistance, it's a current limiting series resistance. And in this case, this diode it is forward biased. And coming to the circuit diagram of reverse biased Zener diode, here the anode terminal of the Zener diode is connected to negative terminal of the battery, and cathode it is connected to positive terminal of the battery. And here also we are using 9.1 volt breakdown voltage Zener diode, and a 0 to 20 volts voltmeter it is connected across the Zener diode so as to measure the voltage across the Zener diode, and 0 to 20 milliamperes ammeter is connected in series with the Zener diode to measure the current flowing through the Zener diode. And here also we need a series current limiting resistor of 1 kilo ohm. And here 0 to 20 volt meter it is used, since the voltage across the Zener diode it is higher compared to forward biased. And coming to the procedure in forward biased, connect the circuit diagram on the breadboard as per the circuit diagram given. connect the milliammeter and voltmeter of suitable ranges. By varying the supply voltage gradually in small steps and measure the forward voltage Vf in incremental steps and note the current If at each incremental step of 0.1 volt and tabulate the readings. Draw the graph between Vf and If taking Vf on x-axis and If on y-axis and calculate static and dynamic resistances of the Zener diode. And coming to reverse bias, arrange the components on the breadboard as per the circuit diagram given. Connect the milliammeter and voltmeter of suitable ranges. By varying the supply voltage gradually in steps and measure the reverse voltage Vz in incremental steps and note down the current Iz at each incremental step of 1 volt, tabulate the readings. Draw the graph in between Vz and Iz by taking Vz on x-axis and Iz on y-axis. Calculate the reverse resistance of the Zener diode and identify Zener breakdown voltage. And these are the tables used to tabulate the readings. And for forward bias, we need to write source voltage, forward voltage, and forward current. And whereas for reverse bias also we need to write down, tabulate the source voltage, reverse voltage, and the reverse current. Here the forward current and reverse current both are in milliamperes range, since this Zener diode, it is a heavily doped diode than the ordinary diode, and it can be operated in the breakdown region. And this is the model graph. Up to certain minimum voltage, the current flowing through the diode, it is 0. That voltage we can call it as a cut-in voltage. After the cut-in voltage, a small change in voltage creates a large change in current, and hence the forward resistance is very small. Here Vf is positive, If is positive in forward biased case. That's why we are getting these forward characteristics in the first quadrant. And here the cut-in voltage of the Zener diode, it is slightly greater than the cut-in voltage of the normal diode, since the Zener diode, it is a heavily doped diode. And coming to the reverse characteristics, Iz is negative and Vz is also negative. So we are getting the characteristics in the third quadrant. Here, if the applied voltage is less than the Vz, then a very small reverse saturation current it is flowing through the Zener diode, and it is almost constant. If the applied voltage is slightly greater than the breakdown voltage, then a very large current is flowing through the Zener diode, but the voltage across the Zener diode, it is almost constant, that is Vz. That's why the Zener diode, it can be operated in the breakdown region. In the breakdown region, we are getting a constant voltage across the Zener diode. That's why the Zener diode, it can be used as a voltage regulator. And from this graph, similar to the diode forward and reverse characteristics, here also we can calculate the static and dynamic resistance. Static resistance means the resistance at a particular point, and the dynamic resistance means the change in voltage and the change in current. Change in voltage and change in current gives the dynamic resistance. And coming to the calculations, I already told static resistance, it is the voltage at a particular point, means select one operating point on forward characteristics, the corresponding voltage and current, it gives the static resistance. If this static resistance, it is in tens of ohms. So dynamic resistance means select 2 points close to each other, and the corresponding change in voltage and change in current, it gives the dynamic resistance, and it is also in the tens of ohms range. And the cut-in voltage, it is slightly greater than the normal diode, which is 0.7 volts. Coming to reverse bias, for reverse bias also we need to calculate static and dynamic resistances. Static resistance means the resistance at a particular point, and dynamic resistance, the change in voltage by change in current on the reverse characteristics. And the breakdown voltage, it is 9.1 volts. And coming to experimental setup, this is the experimental setup for Zener diode forward and reverse characteristics. Let's move on to experimental setup. Setup for Zener diode characteristics. And this experiment, it requires a breadboard, 1 ammeter, 1 voltmeter, and 1 RPS unit. Set the initial conditions in the RPS unit, means this current knob must be in maximum position and voltage knobs must be in minimum position.
The positive terminal of the power supply it is connected to anode of the Zener diode. And negative terminal it is connected to cathode of the Zener diode. And hence this Zener diode is said to be forward biased. If the Zener diode is forward biased, the voltage across the Zener diode it is very less. That's why we are using 0 to 2 volts range voltmeter. And the current that is flowing through the Zener diode is very high. That's why we are using 0 to 10 milliamperes ammeter. The procedure for this experiment forward characteristics, it is same as that of the diode forward characteristics. Vary the supply voltage and note down the corresponding voltage and the current. Similar to normal diode, for this Zener diode also there is a cut-in voltage. Up to cut-in voltage, the current that is flowing through this diode is almost 0. First I am trying to identify the cut-in voltage. So vary the input voltage up to certain voltage. The current is almost 0. And this cut-in voltage of this Zener diode it is slightly higher than the normal diode. So it's almost 0.6. To 0.6 there is no current flowing through the diodes. That's why the cut-in voltage it is equal to 0.6 volts. As the applied voltage it is further increases, the current flowing through the diode it is increases. Similar to the diode, a small change in voltage it can create a large change in the current, and hence the forward resistance it is very small. So vary the applied voltage. A very small change in applied voltage it can create a very large change in the current. So here for 0.7 almost we are reaching 3.6 milliamperes currents. So the resistance it is very small. And this is the tabular form. Vary the source voltage and note down the corresponding voltage and the current. Up to 0.7 the current it is almost 0, that is the cut-in voltage. After the 0.7 volts, a very large change in current because of the low forward resistance. If you reverse the Zener diode terminals, then with this setup we can obtain the Zener diode reverse characteristics. The positive terminal of the supply is connected to cathode of the Zener diode. Negative terminal it is connected to anode of the Zener diode, and the Zener diode it is said to be reverse biased. So here also the procedure it is same as that of the forward bias. By varying the supply voltage, we can note down the voltage across the diode and current flowing through the diode. It's a Zener diode. It can be operated in breakdown region. Initially, for certain voltage, up to certain voltage, the current flowing through the diode is almost 0. Afterwards, as the supply voltage it is increases, the current is also slightly increases. As the supply voltage it is further increases, the voltage across the Zener diode it is constant at the breakdown voltage. Afterwards, as we are increasing the supply voltage, there is a change in current but no change in the voltage across the diode. That's why the diode it can act as a Zener diode it can act as a regulator. Okay. So first I am changing the supply voltage. As the supply voltage changes up to certain voltage, the current that is flowing through the diode is almost 0. Okay. Here we used milliammeter. That's why the current it shows 0. If it is a microammeter, then definitely we are getting some current here. Yeah, the current it is started almost at 8.6 volts, and afterwards, as it is further increases, the current is also increases. So the voltage it is increased and the current is also, reverse current is also increases. As the supply voltage it is further increases, the voltage across the diode it becomes constant. It is constant at 9.1 volts. Why? Because here we are using a Zener diode with a breakdown voltage of 9.1. That's why this voltage it is constant at 9.1. As we are further increasing the voltage across the diode it is constant and the current it is increases. Here this table it shows the reverse characteristics. As we are increasing the supply voltage, the voltage across the diode is increases, but the current initially it is almost constant. Afterwards, as the voltage increases, the current is also increases. As the voltage further increases, it is constant at 9.1 volts and hence it can act as a regulator. If you get the characteristics, these are the forward and reverse characteristics of Zener diode. The forward characteristics it is similar to the normal diode characteristics with a slightly increase in cut-in voltage. And whereas the reverse characteristics also similar to the normal diode, but this Zener diode it can be operated in breakdown region. Initially for certain reverse voltage the current is almost zero. Afterwards, as the voltage it is increases, the voltage across the Zener diode it becomes constant. And for this Zener diode also we can calculate static and dynamic resistances. The procedure for calculation of static and dynamic resistances it is same as that of the normal diode. For static resistance calculations, identify one point on the characteristic curve, the corresponding current and voltage it gives the static resistance. And for dynamic resistance calculations, select 2 points close to each other on the characteristics and the corresponding change in current and change in voltage it gives the dynamic resistance. The procedure for calculation of dynamic resistance in reverse bias it is same as that of the forward bias. So this Zener diode it can be used as a voltage regulator.
And these are the practical values obtained from forward bias diode characteristics. Source voltage, forward voltage and forward current. By varying the source voltage, note down the forward voltage and the forward current. Up to almost 0.7 volts forward voltage, almost negligible current it is flowing through the divides. After this voltage, a very large change in current we can observe. That's why the cut-in voltage for this particular diode it is equal to 0.7 volts. And if you calculate the static and dynamic resistances, static forward resistance it is 85 ohms and static dynamic resistance it is 20 ohms. And these are the practical values obtained from the Zener diode reverse bias. And here also by changing the supply voltage, note down the reverse voltage across the diode and the reverse current flowing through the Zener diode. And here up to 9.1 volts across the Zener diode, a very small change in current we can observe. After the breakdown voltage, even though the supply voltage increases, the voltage across the Zener diode it is constant, whereas there is a change in current. And hence the breakdown voltage for this particular diode it is equal to 9.1 volts. And this is the graph from those characteristics. Forward characteristics we can obtain in first quadrant and reverse characteristics we can obtain in third quadrant. And after the cut-in voltage, a small change in voltage it can create a large change. If the applied voltage it is greater than the breakdown voltage, then almost constant voltage we can obtain across the Zener diode, but there is a very large change in the current. And these are the discussion questions. Give a statement on doping concentration by comparing cut-in voltage of Zener diode with the PN junction diode. Comment on forward static and dynamic resistances of Zener diode by comparing it with PN junction diode. Comment on reverse static and dynamic resistances of Zener diode by comparing with the PN diode. What do you understand about Zener breakdown voltage? And coming to the summary, in this demonstration of Zener diode, we have learned to draw forward and reverse characteristics, calculate static and dynamic resistance, obtain cut-in voltage, obtain Zener breakdown voltage.